like interviews with the people who had been evicted.
Aw.
Yeah, Lamau. That's what they get. Emily, don't frown.
Did they play like sad piano music?
They got what they deserved. Okay. All right, let's look at, let's do a problem together. That's what we want to do. Physicos. Mr. Teletubby's out once again. Okay.
Not for long.
What do you mean?
Julia, be optimistic.
Bro, we got the forecast is 2 yellow circles today and tomorrow.
Yeah, but.
I don't see a cloud in the sky,
Saturday and
Julia.
Sunday.
Is there a cold front coming?
Yes.
Yay!
No.
Why am I gone for
Okay, so let's look at 16. Let's read it. It says, by the way, what are we doing with these questions? What's the word? Starts with a K.
Knowledge.
No, not knowledge. When you're just describing the movement of things.
Kinematics.
Kinematics. Notice there's been no talk of forces, right? There's been no talk of forces, mass, things like that. That's really the physics. This is still physics, but kinematics is purely studying motion, right? So keep that in mind. Everything we're doing is just kinematics, but in the angular realm. So, okay, if a disk starts at rest and experiences a constant angular acceleration of 6 pi radians per second squared over a 10-second interval, can we answer some questions about that system? So, like, is the answer to the first question an easy peasy or a not easy peasy?
It's,
I'm feeling that.
This is easy. So, and there's a bunch of ways that something could experience an angular acceleration. You could, I don't know, hit it with a air dryer. Is the word air dryer? No, it's
dryer.
hair dryer. Hair dryer. You could, or a magnet or something if it was magnetic, or it could just be a ramp. We're going to move on to that pretty soon. Is analyzing like, what happens if you roll something on a ramp. It's not quite the same as a frictionless block. So they're giving us what symbol do we assign to the 6 pi?
radians per second squared.
Right, but what symbol is that?
Acceleration.
Alpha. Mr. Fishy.
Fishman.
Fishman. Okay, alpha. I hope this is visible here. Yeah, okay, it looks like you can see it. So alpha is 6 pi. All right. Okay. It was initially doing what? What was its initial state?
Resting.
It was at rest. So initially, it's at rest. You okay about that?
Yeah.
And then we don't know this yet. We're going to find it. So how can you find the final omega if you know this? And there's one other piece of information we know. 10 seconds. So there's a formula we have, or I mean, I hope you just know this by, this is a good little way you can kind of assess your own understanding here. If the answer is obvious to you right now, what this is, then it's probably, at least partially at least clicked in your head what's going on. If not, it's okay, you're just, maybe you're still relying on the formula. Who knows the answer? Who doesn't know the answer? 60 pi, right? Because acceleration times time would give you the change in velocity, right? Let's say you're not there yet. That's fine. You just go, we wrote a formula for this, right? Your final speed is your initial speed plus acceleration times time, right? You hopefully have that at the bare minimum, you got to have that in your notes or something, right? So, so your final speed would be 0 plus 6 pi times 10. By the way, so at the end, put this into simplest terms. At the end of this, how fast was he rotating? 30 spins per second. Pretty fast, right? Do we understand that? So this is 60 pi. Now we want to know how many revolutions did the disk make while it was speeding up? So how many times would it have rotated going from here to here. That was a very sneaky way to do this. I'm curious if anyone knows what sneaky is.
Time.
What? It involves time. Just wondering, does anyone think they know the answer just through pure thinky winkies? Was that or you just? All right, well, that's okay, we'll come back to it. Let's just use the formula. How about the formula? So the formula we wrote, the big one, we put a big box around it, is that the total number of radians spun is omega naught t plus 1/2 alpha t squared, right? Everyone okay with that? And once we get that, because we know all these numbers now, right?
Yes.
And once we got that, what are we going to do? Once we know how many total radians it turned, what will we do? Divide by 2 pi, right? So let's do that. So omega naught was 0, so 0 times 10, t is 10, plus 1/2 times 6 pi times 10 squared. What does that come out to be?
Uh, 300 times.
105. So the number of turns, number of rotations would just be how many radians you turned. Are we sure we're all okay with this idea? Mm-hmm. By the way, does anyone know there's a more famous formula that basically says the same thing as this. Like suppose instead of number of turns total, I wanted to talk about number of turns per second, like a rate. What letter is number of turns per second? T is number of seconds per turn.
Yeah.
F, the frequency is number of, so if I divided these both by time, right? This is just kind of an aside here, but number of turns per second is called the frequency. How about number of radians per second? What letter is that? Omega.
Make some note cards.
Yeah, some of you guys might need to study a little bit outside of class. I mean, there's only so much I can do for you up here. Like, at a certain point, you gotta get that elbow grease, right? Like so just let me throw this out there. You're gonna be lost if you don't really understand what is frequency, what is period, what is angular velocity, what is angular acceleration. Those are the big four, really. But does this look familiar? Okay, now these say basically the same thing. This is the total number of turns, is the total number of radians divided by 2 pi. This one just says the number of turns per second is equal to the number of radians per second divided by 2 pi, which you can also, of course, write that as omega equals 2 pi f. That's the other way. So I think the first time we wrote it, we just wrote omega equals 2 pi times f, same thing. Okay, so anyway, the answer then is that divided by 2 pi is 150 revolutions. Okay, now I want to go over the sneaky, what I think is a more interesting way of thinking about it. What was the rotational rate at the beginning?
Infinity.
No, the period was infinity, but the rotational rate, how many rotations per second?
0.
0. What was the rotational rate at the end?
Well, no,
Yeah.
divide.
30.
30.
At the beginning it was making 0 spins per second. At the end it was making 30 spins per second. So it stands to reason that the average number of spins per second. Now you have to understand that this is linearly increasing, which may not be obvious, but it is. Because if omega, do you see, is omega increasing linearly? Yeah, that's a linear equation. And frequency is just omega divided by a number, so frequency is also increasing linearly. So the frequency, if you did frequency versus time, it's going from 0 to 30 over a 10-second period. And so, by the way, if you go revolutions per second multiplied by seconds, that would give you revolutions. A calculus fam. Actually, physics fam too, because we've gone over this principle, right? The area under the curve gives you F times T. So the area of that triangle is 150. Or maybe you thought of it as, well, the average, right? The average rate is 15, halfway between 0 and 30. 15 times 10 is 150. Fork knife, Tilted Towers, Retail Row, Pleasant Park, Julia? No? Just trying to name some of your favorite places. Okay. Me and Paige devastated. We can't go get our dogs anymore. It's fun. The couch co-op is dying, unfortunately, which is very sad. Yeah, so like there's not that many games out now that you can play 2 players and 1 TV. And it's like, bro.
You just create it. You start coding.
Yeah, you go create your own game.
Yeah.
Or just buy 2 TVs
Or
or
just
side by
play
side.
Blackout 1 and Modern Warfare for other years.
We've thought about that, but you have 2 TVs, then 2 Xboxes, and 2 Xbox Live accounts. So it gets
Just like that loadout.
Well, sign in on the scale. I mean, I don't really understand it all, but you can't like this like base.
in the olden days of like N64, almost not every game, but most games came with a mode where you had 2 controllers plugged into your game,
Yeah.
and your TV would either split it this way or split it this way, and you'd both be playing either against each other or together. My wife and I like to play together on the same teams. But anyway, that's dying now because a lot of people don't do that anymore. In the old days, it would be like, oh, you'd be like, oh, I have a PlayStation or I have an Xbox, and your friends would come over and you'd play together. But now with the internet, high-speed internet, you can just be like, well, I'm at my house, you're at your house. So it's
Sharing support as a society. Sharing support is.
yeah, we do be living in a society. I agree. Right, Julia? They don't think it'd be like it is, but it do. Right, Julia?
That's a great.
That's a great. My family still has the original Xbox.
Yeah.
With like the 4 controller. And
Dude, original Xbox playing Halo 1 with my older brother, and he would just kill me over and over. And I could I'd finally get like 1 kill, and it was the greatest thrill of victory ever. Just like kill him 1 time.
I remember.
See, my brother would be like, "Oh, you got 1 kill on me," and I'd be like, "Yeah, are you proud of me?" He goes, "No," and then you'd be like, "Punch guy." And I'm like,
Well, if your brother knows the map like by heart, and you have no idea where you are, he knows because he can see the screen. He sees where you are. He knows exactly where you are. Jumps out behind you and shoots you, and you're like, well, okay. So then it makes it challenging. So
That's why couch co-op is dying.
no,
my brother was
you have to agree ahead of time. Can you look at your opponent's screen or not? Because sometimes you say, well, yeah, we agree. We're both going to look at each other's screens, try to get an advantage. Or you have to promise not to, I guess.
Well, even if you promise, you normally look at it.
All right, let's look at 17. All right, so if a disk starts at rest and experiences a constant angular acceleration of pi/2 radians per second squared. Now, this is an exercise in and of itself. If alpha is pi/2, think about what that means. Think about what that means. What does that mean? What is happening every second? It's gaining a quarter of a turn per second of speed. Yes. So if you looked at, say you made a chart and went, here's time, here's omega. This one's pretty easy to do, right? Time 0, it says it's at rest. Time 1, okay, add pi/2, add half a pi. Time 2, add another half a pi. Time 3, add another half a pi. Get the idea? Time 4, add another half a pi. But you could also think of it, I think what's going to be more beneficial is to really think about what's happening to the turning rate, the frequency. So initially he's making no turns per second. After 1 second, it's like Aiden said, pi/2 is a quarter turn, right? So after 1 second, his rate is a quarter turn per second. After 2 seconds, he's making half a turn per second, then 3/4 of a turn per second, then 1 turn per second, and so on. Do we understand?
Yeah.
Okay.
I swear to God, I see these people at stoplights.
What?
People that take off at 1/4 of a turn, 1 second, half a turn, 3/4 of a turn. They don't take off very fast yet.
I feel you. Yes.
Okay, I didn't know if you were getting that. I'm sorry.
That feel when you're in Whitefish and the light turns green and you're 10 cars back, and then it turns red before you get
Yeah,
the
yeah.
first
Yeah,
car.
the light,
That's-
turn lanes Whitefish are like 3 seconds.
Okay, so anyway, just keep in mind though, this is not the total number of turns, right? It would be wrong to say that I've made 1 total turn. This is the turning rate. So just at time 4, the rate happens to be at that moment 1 turn per second. So what you got to do here, what formula do you think we're going to use if we know this, right? We know completes its 35th full rotation. So 35, let's just say, how long does it take to make 35 full rotations? What's another way of saying 35 rotations?
Oh, 35.
70 pi radians. Yeah. Feel okay about that? Now, why would I want that? Well, I got this nice formula that relates angular displacement to time and alpha and stuff. So write that formula out. And then ask yourself, do I have everything I need to solve this? Do we have everything we need?
Yeah.
I think we do, yeah. There's one unknown. What does that reduce down to, though? It's the second to last line. You've got 70 pi equals pi divided by 4 times t squared. What happens to those pi's?
Inflow.
Yeah, divide both sides by pi, and then multiply both sides by 4, and you get this. And you're going to get, I don't know, some weird number. 16, maybe? 16 point. All right. So what's the idea here? I mean, you can probably tell from the answer that there was not really an easy way to answer this question. There was no like intuitive, simple argument you could make to figure this one out. You have to kind of use this derived formula. All right, let's look at maybe one more. And so let's look at, I think 21 will be interesting. 21's a bit of a riddle. They're a bit of a puzzling one. The other ones I think should be pretty straightforward for you. I don't think you're going to run into too much confusion on them. By the way, just a quick little side thought here. Do you guys remember the time-independent kinematics formula? Remember what that was for? Why it was useful? Suppose you don't have it memorized, but you remember. I would hope you remember that one exists, and maybe in what case would you maybe look that up? Why would you want to? What kind of scenario would you be dealing with where you'd be like, oh yeah, I should use the time independent formula? You could. Well, I'm thinking more generally. Think about the name, time independent.
Something without time.
If time's not involved. So say you have information about, like, say, starting velocity, ending velocity, and acceleration, or say starting velocity, ending velocity, and distance.
Maybe you don't
No,
have time.
Yeah, so say you have a problem and there's no mention of time. If you Googled it, you'd find, okay, there's this formula. That ring a bell?
Yeah.
I'm just throwing this out there. If you were wondering, since we're doing kinematics, I didn't really include it on this problem set because I felt like it's kind of a weird one to. It doesn't come up that often with like rotation, but anyway, if you're wondering, yes, there is one for rotation. Isn't that neato?
Yes.
It's the exact same formula. Exact same formula. So that's kind of neat. So we're going to start seeing this a lot as we study rotation. Is everything we've already learned has like an analog in the rotation in a rotational model. So like Newton's law, F equals ma, has a rotational. Which is a fun trivia question, actually. I wonder if anyone knows one of these answers. You guys remember Newton's second law, right? F equals ma.
Yeah.
There's a the rotational version is going to end up being, instead of force, who knows what's the rotational version of force?
Momentum.
No.
Torque.
Yeah, that makes sense.
Torque. Guess what the rotational version of acceleration is? Alpha. You didn't know that one.
What's the rotational version of that?
It's called moment of inertia. I would be surprised if anyone's heard of that.
I've heard the word.
Oh, you have moment of inertia?
Inertia.
Oh, okay, nice. So anyway, so that stuff's coming. Same with energy. There's kinetic energy for if a thing's moving. Well, what if it's spinning? You have rotational kinetic energy. Okay, sorry. Let's get to 21. Meme number. You get it? 21. Remember that meme, Kate? It was so epic. A cylinder with a radius of 20 centimeters. This drawing's not to scale. The radius,
Big
though.
cylinder.
Oh, it's not that big, is it? Fine. It's medium size. I'll grant you that it's medium size. Okay. This is a 12-meter long ramp. And it takes 6 seconds to roll all the way down the ramp. So we timed that with stopwatch. The question is, first, how many times would that rotate as it rolled down the ramp? I'll give you a hint on this one. This one is not. The fact that this question is being asked in this context actually makes it harder, but this is actually a very simple question. Yes.
You just find the circumference and then divide 12 meters by.
Very good. Did you catch that? Okay. The reason this is kind of a tricky question is this is kind of a meme-maze in like math and physics and stuff. Is you can throw an easy question into a difficult context, and then people will often forget, like, oh, I can just use simple geometry, right? So he's going 12 meters. Every turn is just the circumference. So my circumference is 2 pi times 0.2. Let's get a decimal for that. Although maybe a decimal is not. Let's see what happens without a decimal, and then go from there. So as a non-decimal, it's right in terms of pi, it's 0.4 pi. Okay, so if I go 12, so number of turns would be 12 divided by 0.4 pi, which is 30, well, 30 over pi. Because just do the 12 divided by the 0.4, you get 30. So roughly how many turns? 10. Yeah, roughly 10ish. It's like 9 point something. 5. Okay, so we get that. That's fine. Okay. Because each turn is just a bit more than a meter. And then, okay, then what was, we got, that's answer A. Now, why might you want to keep the pi in there?
Angular velocity.
Yeah, because what's the angular velocity then? Or what's the total number of radians turned then? You multiply the number of turns by what? 2 pi. So what's that times 2 pi? Just 60, just the integer 60. So, okay, what was the cylinder's average angular or linear velocity? We can get the linear velocity really easily. Do you see it? For average. The average would be, do we see?
12 divided by 6.
3 meters.
It's the displacement, 12 divided by the time. So you just go 12 meters divided by 6 seconds. So the average velocity was 2 meters per second. Let's think about this. What do you think the final velocity was then? How fast was he moving down here, you think?
12 meters a second.
4 meters per second. Because he was going 0.
Yeah.
Remember, your average is halfway between your initial and your final. So if your initial is 0 and your average is 2, your final should be 4. Assuming it's linear acceleration or constant acceleration, which I guess, spoiler alert, it is. If you're rolling, it's just like a frictionless block. It's going to still be a linear increase in velocity. So, okay, and then what's omega then? Omega average. Well, let's not overcomplicate this. Well, there's a couple ways you could do this, I guess. You could go number of radians turned divided by, right? So how many radians did we turn? Yeah, you take the number of turns multiplied by 2 pi, which we can see is 60. So 60 radians divided by how many seconds? 6 seconds. So it must have been 10 radians per second. How else might we have gotten that number? How else can you get, what's another really, really important equation that relates omega to V to R? For those of you that need to brush up and do a little bit of studying, make sure that's on your study list. V equals omega R. That's an important one. Okay? Are we fine with that?
Yeah.
Okay, so I could have gone V divided by R, right? So I could have done V2 divided by 0.2, which would have made 10. Okay. For C, I've already touched on that, right? C, what's the final, if this is the average angular velocity, and we started at rest, what's the final angular velocity? 20. What's the final velocity? 4. Now you can calculate the acceleration, right? Because how do you calculate acceleration then? So if your V final was 4, And what does that mean for your acceleration? We went from 0 to 4, right? So that's my change in velocity divided by the amount of time it took, right? So your acceleration would be 2/3 meter per second squared. How about this? Your final omega was 20 radians per second. So that tells you that your alpha, remember 2 options here, right? I can either divide, what can I divide this by to get the answer? Radius, yeah, because just like this, A is equal to alpha R. So if I have A and I have R, then I have alpha. Or I can just use the final omega, right? That's another option. I can go 20 divided by 6. So 10/3. Sorry, radians, it's radians per second squared, sorry. Radians per second squared. All right.